All right, folks, today I want to talk about something really cool. First off, if you've been keeping up with the news over the past couple of days, you'll know that OpenAI will ban you if you ask ChatGPT O1 a very specific question. For those that haven't heard, the banned phrase involves asking ChatGPT O1 to explain its reasoning process in detail, step by step. Basically, it seems like OpenAI isn't too keen on revealing how this new O1 actually works. However, that's where Google DeepMind comes in to save the day. Thanks to a really interesting paper, they've shed some light on a few cool aspects of ChatGPT O1. We'll be covering as much of it as possible throughout the entire video, and let me know in the comments at the end of it what you think about all of this. First off, folks, to get a sense of where all of this fits, let's backtrack a bit. Over recent years, models like GPT-4, Claude 3.5 Sonnet, and others have skyrocketed in capabilities. They generate human-like text, answer complex questions, help us with coding, tutoring, and even tackle philosophical debates, and it's really incredible. But here's the kicker. As they get smarter, they also become more resource intensive. And scaling up these models, making them bigger and more complex, needs huge amounts of computing power, which, of course, drives up costs, energy use, and generally just slows things down, especially when you need real-time results. And it's not just about infrastructure, because, for example, pre-training these giants takes massive data sets and months of work. So rather than just building bigger models, maybe there's a smarter way forward, and this is where optimizing test time compute comes into play. Instead of creating a one-size-fits-all model by making it bigger, what if a smaller model could be designed to think more effectively during inference? This could totally change how we use AI, especially in situations where resources are tight but performance still matters. Okay, so onto test time compute versus model scaling. As I said in a previous video, test time compute is basically the effort a model puts in when it's delivering answers, not when it's being trained. Think of training like a student cramming for an exam. All the learning happens there. Test time is the exam itself, where the model uses everything it's learned to solve problems or answer questions. So why does test time compute matter? Right now, models like GPT-4o and Claude 3.5 Sonnet basically are built to be powerhouses right from the start, and this means they have to be enormous. But scaling these models to such massive sizes obviously has its downsides. First, there's the cost, folks, because more parameters mean more computing power, and that translates to higher expenses, both for training and using the model. But it's not just about money, because these models also eat up a ton of energy, which isn't exactly eco-friendly. Then there's the challenge of deployment, because these giant models are tough to use in places with limited computing resources, like mobile devices or edge servers. So the real question is, can we get the same or even better performance without having to build bigger models? That's where optimizing test time compute comes in, folks, and it's pretty cool. Basically, by using computational resources more efficiently during inference, we can potentially improve performance without needing to supersize the model. For the past few years, the go-to method has been pretty simple. Just make the models bigger. And this means adding more layers, neurons, and connections to boost the model's power. And it's worked. GPT-3, with its 175 billion parameters, was a huge leap from GPT-2's 1.5 billion. And models like GPT-4o keep pushing the limit of what natural language processing can do. So more parameters usually means a more capable model. One that can handle more context, generate more nuanced responses, and perform better across different tasks. But this bigger is better mindset comes at a steep price tag. Training these massive models takes vast data sets, sophisticated infrastructure, and months of work on thousands of GPUs. Plus, using these models in the real world is also expensive, and every single time you ask a model a question or get it to generate text, it needs a ton of compute power that costs and adds up very, very fast. This is basically why companies like OpenAI and Google are exploring smarter ways to get high performance without just pouring more compute and data into the mix. Now, think about the trade offs between these two approaches: scaling model size versus optimizing test time compute. Scaling up is a brute force strategy. It works, but it's costly and inefficient. As models get bigger, the performance improvements start to level off. There's a diminishing return, while the costs keep climbing, so it's not exactly the best return on investment. On the flip side, optimizing test time compute offers a more strategic approach. So instead of relying on gigantic models, we could use smaller, more efficient ones that apply extra computation only when it is needed, boosting performance at the right moment. It's like a sprinter saving every bit of energy for the final push when it counts the most. All right, that's all fine and well, but what does this mean in practice? Basically, the big takeaway is that there's a balance to be found. In some cases, throwing in more parameters might still be the best option, especially for highly complex tasks where brute force is required. But for many other situations, particularly with less complicated tasks or environments with limited resources, optimizing test time compute could be a game changer. And this is exactly what DeepMind's research is digging into: how to strike the balance and what techniques can maximize every bit of compute. All right, that's a bit long-winded, but now that we've laid out the groundwork by comparing test time compute with model scaling, let's dive into some of the key concepts from this research, folks. The team developed two main methods to scale up computation during the model's usage phase, what we call test time, without needing to increase the model's size. The first method is called verify-reward models. Okay, sounds technical, I know, so here's an easy way to think about it. Imagine you're taking a multiple choice test, and after each question, a genius friend checks your answer, and he doesn't just tell you if it's right or wrong. He actually helps you figure out the reasoning that got you there, and this allows you to improve for the next question. That's essentially what a verify-reward model does for large language models. So this process-based approach, checking each step, not just the final answer, helps the model be more accurate by ensuring its reasoning is sound at every stage. It's like having a built-in quality control system that allows the model to refine and improve its answers as it goes. In practical terms, this means a model doesn't have to be massive to be smart. It just needs a good system for checking its own work. The second method is called adaptive response updating. Now, think of this like playing 20 questions. Each new question adapts based on the previous answer. If you know it's a fruit, you stop asking about animals. In a similar way, adaptive response updating lets the model refine its answers as it goes, learning from what it got right or wrong previously. Example: when the model gets a tough question, it doesn't just give one answer and move on. Instead, it revises its response multiple times, taking into account what worked and what didn't from earlier attempts. This lets the model think harder or smarter when faced with complex problems, instead of just jumping to a conclusion. Okay, now let's tie these two methods, verify-reward models and adaptive response updating, together with something called compute optimal scaling. Now, don't let the name scare you. It's all about using computing power wisely. Instead of applying the same amount of compute power to every problem, this strategy allocates resources based on the task's difficulty. Imagine running a marathon. You wouldn't sprint the entire way. You'd pace yourself, running faster in tough sections and slowing down when things got a little easier. That's what compute optimal scaling does for models. If the problem is simple, the model can breeze through it with minimal compute. But if it's tough, it will use more power, like sprinting in important sections of a race, to find the best answer. To test the effectiveness of this technique, DeepMind's researchers used a challenging dataset called the Math Benchmark. It's a collection of high school level math problems from algebra to calculus, designed to test deep reasoning. The idea is not just to get the right answer, but to understand the steps needed to solve it. They use the Palm 2 models, fine-tuned for two specific tasks: revision and verification. Revision involves training the model to improve its own answers iteratively, like a student going through their homework and correcting mistakes. Verification is all about checking each step to ensure accuracy, similar to a teacher reviewing the student's work. Next, they introduced process reward models, PRMs, and adaptive research methods. PRMs help the model verify each step of its reasoning, predicting whether each move is correct based on prior data. This is like getting hints during a puzzle, making the search for the right answer more efficient. It allows the model to adjust in real time, navigating toward the correct solution more effectively. In short, compute optimal scaling adapts the model's compute use based on task difficulty. This method can deliver similar or even better performance using 4 times less compute compared to traditional models. In some cases, a smaller model using this strategy can outperform a model that is 14 times larger. This approach is similar to OpenAI's O1 model, which also focuses on smarter compute usage. O1 ranks highly in competitive programming, scores among the top 500 in math competition, and exceeds PhD-level accuracy in scientific questions. So when you take all these moving parts and you put them together, you start to get an idea of how powerful O1 really is. Okay, folks, hit that like and subscribe button if you found this video insightful, and let me know in the comments what you think about all of this. As always, see you in the next one, folks. You all take care.